Hello everybody, welcome to today's lecture for the Material and Energy Balance course. In the last lecture, we looked at some of the basic concepts and terminologies associated with energy balances. Today, we will have a brief introduction for how to perform energy balance calculations for closed and open systems. So, let us first start with law of conservation of energy. What is the law of conservation of energy? It is basically stated as energy can neither be created nor be destroyed, it can only be changed from one form to another. This is based on well founded experimental evidences which have proved that any amount of energy which is gained by a system would be exactly equal to the amount of energy which is lost by its surroundings. So, based on this, we have established something called the first law of thermodynamics. The first law of thermodynamics is nothing but the law of conservation of energy. And from this concept, we will be performing many energy balances. Just like how we performed material balances for different types of systems, here we will be performing energy balances for different types of systems. This will again be like a balance sheet or an accounting for energy which is supplied and removed from a system. For performing these calculations, we will do this only for systems that are homogeneous and not charged without surface effects, so that we can keep the calculation simple. When we add these complexities, the problems become much more difficult and cumbersome, which we will not be dealing with throughout the course. It will also be applied at a macroscopic viewpoint. Although the law of conservation itself applies for microscopic levels, we will not be performing calculations at the microscopic levels. All our calculations will be for macroscopic systems. All equations which we will be using will represent the cumulative quantities over a time interval which is taken as the period of time for observation. Now that we have understood what our constraints will be for performing energy balances, let us refresh the different forms of energy. So, we classified the forms of energy based on how the energy is used either to transfer between the system and the surroundings, or if it is an inherent energy possessed by the system. So, the different types of energies which are used to transfer energy from the system and the surroundings is called as heat and work, and the inherent energies possessed by the system are kinetic energy, potential energy and internal energy. Points which we need to remember when we perform energy balance calculations are: heat is 0 if the process is adiabatic. We already looked at what an adiabatic process was. It is defined as a perfectly insulated process where there is no exchange of heat between the system and the surroundings. When such a process exists, then we would have to account for Q, which is the heat, as 0. While we perform energy balance calculations, the term for heat, which is the energy transferred between the system and its surroundings due to temperature difference, will be considered to be 0 for such systems. Work is basically the movement of the system boundary against a resisting force. This could either be movement of a piston or rotation of a shaft and so many other things. You can also have passage of electrical current or radiation across the system boundary, which can also cause work. As I had already mentioned in the last lecture, we will not be looking at electrical energy as part of this course. As chemical and biochemical energies are primarily governed by thermal and mechanical energies, we will focus our goals and calculations within those parameters. If there are no moving parts or electrical currents or radiation in a system, then we would have to assume work done by the system or on the system to be 0. That would mean W would be 0. Then we also have the terms where the energy is possessed by the system. The kinetic energy would be considered to be 0 if the system is not accelerating. So, please understand, it is not that the system does not have to move. The system could actually be in motion as long as it is not accelerating, which means the velocity of the system is not changing. The change in kinetic energy is 0. So, the change in kinetic energy is what we will be using for performing energy balance calculations. So, this change in kinetic energy will be 0 for non-accelerating systems. Potential energy would again be the change in potential energy, which means as long as the position of the system is not changing, that is, the system is not rising or falling, then change in potential energy will be considered to be 0 for performing energy balance calculations. The last energy which is possessed by the system is the internal energy. This internal energy, as I already mentioned, depends on the chemical composition, state of aggregation or the phase, and the temperature of the system. It is independent of pressure for ideal gases, and it is almost independent of pressure for solids and liquids. So, by this what I mean is, whenever we have a process where only pressure is changing, then we can ignore the effect of change in internal energy for ideal gases and solids and liquids for the most part. If temperature and phase change does not happen, then you would have to assume delta U equals 0 or change in internal energy is 0, as long as reactions are also not happening. So, in case of systems where pressure changes are very high, there could actually be a small effect of change in internal energy for solids and liquids. Even in that case, it will be 0 for ideal gases. So, we would use delta U to be 0 in most cases when pressure changes are happening in the system, because most of the times changes in pressure are small and the effect of this change in pressure is numerically very small. So, now that we have these points which we have to understand and apply, let us move on to performing energy balance calculations. Let us first start with a closed system. As I had already mentioned, in our material balance calculations, we were only talking about open systems most of the times, because in an open system the material was crossing the system boundary. In an energy balance, you can have energy crossing the system boundary even in closed systems. So, understanding how to perform energy balance calculations for a closed system is crucial. We need to understand that there is no mass flowing in or out of the system. Energy balance for this would be written like input minus output equals accumulation. So, you do not have generation and consumption terms for energy, because energy can neither be created nor be destroyed. So, this means input and output are the only terms which you would have, and accumulation will go to 0 at steady state. So, energy can be transferred from one system to the surroundings or from the surroundings to the system. This means there would always be input and output terms, and energy can be transferred in terms of heat and work, which we already saw, and accumulation would basically be the difference between the final and the initial energies of the system. Energy balance equation will basically look like this. You would have final system energy minus initial system energy, giving you the net energy transferred to the system. So, initial energy possessed by the system would be 3 components: internal energy at the initial condition, kinetic energy at the initial condition, and potential energy at the initial condition. The summation of all these 3 energies gives you the total energy possessed by the system at the initial condition. Similarly, the final energies of the system would again be the summation of internal energy at the final condition, kinetic energy at the final condition, and potential energy at the final condition. Energy can be transferred between the system and the surroundings in the form of heat and work. So, do you remember the convention we agreed to use? Yes, heat would be positive when it is supplied to the system, and work will be positive when it is done by the system. So, we will use this convention for the rest of the course. So, based on that, energy transferred would be Q minus W. So, the energy balance equation can be written as delta U, which is UF minus UI, plus EKF minus EKI plus EPF minus EPI equals Q minus W. So, this equation then becomes delta U plus delta EK plus delta EP equals Q minus W. So, this is the first law of thermodynamics for a closed system. Each term here represents the respective net cumulative amount of energy over a time period of observation, which could be from time t1 to t2. This is not energy per unit time. So, let us look at an example problem which would help us understand and perform energy balance calculations for a closed system. Here is the example. An ideal gas which is contained in a cylinder is fitted with a movable piston. The initial gas temperature is 25 degrees Celsius. The cylinder is placed in boiling water with the piston held in a fixed position. Heat in the amount of 2 kilocalories is transferred to the gas, which equilibrates at 100 degrees Celsius. The piston is then released. The gas does 100 joules of work in moving the piston to its new equilibrium position. the final gas temperature is still 100 degrees Celsius. Write the energy balance equation and solve for the unknowns. Assume that the gas is the system and ignore change in potential energy due to the movement of the piston. So, if you were to look at this problem, what you have is an ideal gas trapped inside a cylinder with a movable piston. So, the first step is heat being transferred to the system, so that the temperature of the gas rises from 25 degrees Celsius to 100 degrees Celsius, and the volume remains a constant because the piston is not moving. After some point, after this process, the piston is allowed to move, which means the gas expands and 100 joules of work is done on the moving piston, and this results in a final equilibrium position where the piston rests. So, at this condition the temperature is again 100 degrees Celsius, indicating that this is an isothermal expansion process. So, we are asked to calculate the unknowns in the energy balance equations for both these processes. Let us try and do this for this problem. So, the first process is where you have this movable piston. This is at 25 degrees Celsius, it is moved to, the position has not changed, but the temperature has changed to 100 degrees Celsius because there is an addition of 2 kilocalories of energy in the form of heat. We looked at energy balance for a closed system as delta U plus delta Ek plus delta Ep equals Q minus W. So, for this process there is change in temperature, which means delta U cannot be 0. The system itself is not accelerating in any way, so kinetic energy will go to 0. We have been told that change in position of piston can be ignored, but here there is no change in position of piston. So, there is going to be no change in position. So, potential energy will also be equal to 0. Q is not 0 because you have 2 kilocalories of heat being supplied to the system. The piston is not moving in this process, so W will go to 0. So, you have delta U equals Q. So, Q has been given as 2 kilocalories. So, this means delta U equals 2 kilocalories. So, the change in internal energy for the process where ideal gas is heated from 25 degrees Celsius to 100 degrees Celsius by supplying 2 kilocalories of heat is also 2 kilocalories. So, this is a simple calculation, but what I want you to understand here is we first identified that the system was a closed system and then wrote down the appropriate closed system's energy balance equation and cancelled out terms which did not exist, which went to 0, and based on this we were able to calculate the unknowns. Let us look at the second part of the problem where the piston basically, which is remaining here at 100 degrees Celsius, moves to an increased volumes where you again is at 100 degrees Celsius. You have this process which is an isothermal process, and we will have to write the balance for this. So, it is again delta U plus delta Ek plus delta Ep equals Q minus W. So, here there is no change in temperature. So, we know that there is some change in pressure, but we also know that change in pressure does not affect internal energy for ideal gases. This means delta U will go to 0. The system itself is not accelerating or decelerating. So, this means Ek goes to 0. We have been told to ignore potential energy change due to the change in the position of the piston. So, potential energy goes to 0. So, you have only work and heat. So, there could be heat which is released from the system and work which is done by the system. So, we will have to calculate Q as equal to W. We have been told that W equals 100 joules. So, this is positive 100 because the work is done by the gas. The gas expands to push the piston. So, if we are considering the gas as the system, which means work is done by the system on the piston, which is the surroundings. Therefore, you have a positive work, thereby Q is also 100 joules. So, with this we have performed simple energy balance calculations for a closed system. So, again all we did here was identify the right equation for the process and cancelled out the terms that need to go to 0 and finally identified all the parameters that were unknowns. So, this is a simple energy balance calculation. So, we will look at more complicated energy balance calculations in the subsequent lectures, but before we do that we also need to identify and understand another type of system, which is the open system. Energy balances on open systems would also be performed in similar fashion to closed systems, but we need to understand that in an open system mass crosses the system boundary. This would change the energy balance equation slightly. Let us see how it affects the energy balance equation. We first need to understand, as mass enters and leaves the system, we need to understand what would be the work done by the system or on the system when this mass enters and leaves the system. When mass is entering the system, work is actually done on the system, because the mass forces itself into the system to enter the system. Similarly, when the mass leaves the system basically pushes the mass out, which means work is done by the system so that the mass will leave the system. So, these are two work aspects which are brought into the system which were not present in a closed system. So, the net work done by an open system would be the summation of shaft work and flow work. The effect of work because of mass entering and leaving the system is called flow work. Shaft work is the work which is done either to move a piston or rotate a shaft and so on. Change in flow work can actually be calculated as flow work for the system for the mass leaving the system minus the flow work for the mass entering the system. The work in or W dot in would be P in times V dot in, and work which is the flow work for the mass leaving the system would be P out times V dot out. So, when we write a steady state open system energy balance equation, we would have to understand that we will derive an equation based on all the fundamentals we know about the energy possessed by the system and the energy which is used for transferring from the system and the surroundings. Let us start with the general energy balance equation, which would be input minus output equals accumulation. As I had already mentioned, energy balance equations will not have generation and consumption terms. So, at steady state accumulation would go to 0, which means input equals output. So, let us start writing the balance equations for this. Energy which is fed to the system input would be sigma of input times E j dot, where E is the total energy possessed by a component j, and summation of all the energies of different components will give you the total energy of the input stream. In addition to this, you would also have Q dot, which is the heat which is supplied to the system. So, this would be a positive term. You can also have an output equation which is sigma of output of E j dot, which would again be the energies possessed by individual components in the output stream, and the summation will give you the total energy of the output stream, plus W dot, where W dot is the work done by the system. So, because it is work done by the system, it is going in the direction from system to the surroundings. So, it is the output. So, energy transferred from the system to the surroundings. Substituting these two values in the equation we had, basically saying input equals output, we would get sigma input of E j dot plus Q dot equals sigma output of E j dot plus W dot. So, this equation then becomes sigma output of E j dot minus sigma input of E j dot equals Q dot minus W dot. So, from here we now need to identify the energies possessed by the systems in the output and input condition. In this equation we need to identify what E j and W dot represent. E j dot is basically the energy possessed by the component j. So, which would include internal energy, which is U dot j, plus kinetic energy, which is E k dot j, plus potential energy which is E p dot j. Now, converting them to specific internal energy, kinetic energy and potential energy, this equation will become m dot times u j cap plus u square divided by 2 plus g z j. So, where the capital U cap is the specific internal energy, u j is the velocity of component j and z j is the height at which the component j is present. So, this is your total energy of the component j. Now, we have work which is given as W dot, this would contain W s dot and W f dot, where S is the shaft work and W is F is the flow work. So, the change in flow work for a system an open system would be output minus input of flow work. So, you would have flow work output minus flow work input. So, this basically can be written as P j V j cap sigma of this in the output minus sigma input of P j V j dot, sorry, this is V j dot not V j cap. So, this then being converted to specific volume, we can have m dot times sigma out of P j V j cap minus sigma in of P j V j cap. So, this is your flow work. Substituting these two into the equation we had earlier, we would get sigma output of m j dot times u cap j plus u j squared by 2 plus g z j dot plus p j v cap j minus input of the same thing m j times u j cap u j squared divided by 2 plus g z j plus p j v j cap. This would be equal to q dot minus w s dot. So, what I have done here is split the work into shaft work and flow work and taken the term for the flow work to the left side in the equation which we had used. So, the terminology terminology u cap plus p v cap can be combined to form the enthalpy which is H cap. So, this means this equation which we have can then be simplified and written as sigma of out times H cap j plus u j squared divided by 2 plus g z j, all of this times m dot minus sigma of input times m dot H cap j plus u j squared divided by 2 plus g z j would be equal to q minus w s, q dot minus w s dot. So, from here we can basically simplify this equation as delta H dot plus delta E k dot plus delta E p dot equals q dot minus w s dot. So, this is your equation for energy balances in an open system. So, the first term which is m dot times H cap would become the total enthalpy of the outlet stream. The total enthalpy of the outlet stream minus the total enthalpy of the inlet stream forms delta H dot. So, similarly, the total kinetic energy of the outlet stream minus the total kinetic energy of the inlet stream gives you a delta E k dot, and the difference between the total potential energy of the outlet stream and the total potential energy of the inlet stream gives you delta E p dot. So, substituting these values we get delta H dot plus delta E k dot plus delta E p dot equals q dot minus w s dot, which will be used in place of delta u plus delta E k plus delta E p equals q minus w which was used for closed systems. What we need to understand here is, for a closed system, energy balances are performed using internal energy, and for open systems, energy balances are performed using enthalpy. This is because the flow work associated with the flow of a material in and out of the system is accounted for by using enthalpy. So, internal energy plus this flow work ends up becoming enthalpy in the mathematical expression. Therefore, we use enthalpy instead of internal energy while we perform energy balance calculations for an open system. So, here is another example which will illustrate how to perform energy balances for an open system. 500 kilograms per hour of steam drives a turbine. The steam enters the turbine at 44 atmospheres and 450 degrees Celsius at a linear velocity of 60 meters per second and leaves at a point 5 meters below the turbine inlet at atmospheric pressure and a velocity of 360 meters per second. The turbine delivers shaft work at a rate of 70 kilowatts, and the heat loss from the turbine is estimated to be 10 power 4 kilocalories per hour. Calculate the specific enthalpy change associated with this process. Let us perform the calculations for this system. So, this is the flow chart. You have 500 kilograms per hour of steam entering, and the conditions for it is also given, and you have work done and heat supplied to the system, heat removed from the system, and change in height which have also been represented. Let us now perform the calculations. So, as this is an open system, the equation for energy balance would be delta H dot plus delta Ek dot plus delta Ep dot equals Q dot minus Ws dot. So, we already know the value for Q dot and Ws dot which have been given in the problem. So, we need to calculate delta H dot, delta Ek dot and delta Ep dot. So, from the parameters which have been given, we can calculate delta Ek dot, which is the change in kinetic energy, as m dot times u squared, u out squared divided by 2 minus u in squared divided by 2. So, we know the velocities for the inlet and the outlet streams. The outlet stream travels at 360 meters per second and the inlet stream travels at 60 meters per second. So, this means your mass flow rate would be 500 kilograms per hour. So, this needs to be converted to seconds, kilograms per second, because we have the velocities in terms of meters per second. So, this would be 1 hour in 3600 seconds times u out squared, which is 360 squared divided by 2. So, the units would be meter squared per second squared for both. So, this would be 60 squared divided by 2 in the units of meter square per second squared. So, performing these calculations, we can get delta Ek dot as 8.75 kilowatts. So, which is kilojoules per second, which I have represented as kilowatts. Similarly, we can calculate change in potential energy as delta Ep dot, which would basically be m dot g times z out minus z in. So, here there is a drop of 5 meters, which means z out is 5 meters below the z in. So, you have a negative 5 as the change in the height. So, this would become 500 kilograms per hour times 1 hour in 3600 seconds times 9.81 meters per second squared times minus 5 meters. So, this gives you a value of minus 6.81 times 10 power minus 3 kilowatts. Now that we have the potential energy and kinetic energy, we can substitute it back to the equation delta H dot plus delta Ek dot plus delta Ep dot equals Q dot minus Ws dot. By substituting it here, we can calculate delta H dot as, we already know Q dot and Ws dot. By converting them to appropriate units, we can use it in this equation and get delta H dot as minus 90.3 kilowatts. The problem asks us to calculate the specific enthalpy change. So, this is the total enthalpy change for the system. So, we now need to calculate it in terms of specific enthalpy change. This means this value needs to be divided by the mass flow rate. So, this would be delta H cap would be delta H dot divided by m dot. So, m dot here is 500 divided by 3600 kilograms per second. So, you would have minus 90.3 divided by 500 times 3600, giving you a numerical value of roughly minus 650 kilojoules per kilogram. So, this is your change in specific enthalpy. So, from this we have calculated the change in specific enthalpy by using energy balance calculations. So, with this we come to the end of today's lecture. In the next lecture we will talk about performing such energy balance calculations for multi-component systems and also using thermodynamic tables taking values for enthalpy and internal energy from these tables. Until then, thank you and goodbye.